Okay, so what we're going over now is we are going over thermal explosion theory, and we're starting with Seminole theory, which just considered a chunk of energetic material, or you could think of it as a reactive gas in a box, same problem. And in addition to the heat generation from the reaction inside, there is also convective heat loss. There is also convective heat loss that we needed to consider. And an interesting thing about Seminole theory is he was only considered with ignition. And so he was looking in the limit as just as the chemical reaction really starts to sort of take off and go very rapid. And before that happens, the mass fraction of the reactants is essentially a constant at 1. And so we derived from a control volume analysis this governing equation here, which is just a temperature form of the energy equation here, accounting for the heat loss. And I'm not going to show it, but in the notes I have a way that you can do this starting from the fundamental governing equation and adding an external heat loss a source term too. But if you do that, you actually get the same thing, with the exception of the CP here. But for an incompressible solid, a CP and CV are the same thing. Okay, so you wind up with the exact same thing that we did before. Okay, so now we were discussing two scenarios, or what motivated this is that we were looking at the explosion feedback loop, and we basically had two scenarios. One where there's no heat loss, and essentially you could rationalize that for any initial condition, because our box is well insulated that any amount of heat that is any amount of heat that is generated due to chemical reaction is actually going to be stored inside, and then that's going to cause the chemical reaction to proceed faster, which then generates more heat, and then so on and so forth. And if you wanted to stop this runaway process, our only mechanism available to us for this type of problem is to remove heat from the system. And so if we wanted to run forever, basically where the Q dot going out perfectly balances the heat of reaction inside, is that we actually want to look at the conditions that actually lead to a steady state solution. Okay, which means it will run forever and ever and ever and ever. So if we do that, we'd see that we would see that the heat from the chemical reaction is balanced perfectly with any external heat loss. Okay, and so the external heat loss is just Newton's law of cooling, and we divide by the volume, and you can see where that came from in this derivation over here. Okay, and then we had the heat from the reaction, and note that we assume that YR is equal to 1 for this ignition process. And again, that's not the most realistic assumption in the world. And in your homework, you guys will be correcting for that. And there will be some differences, not much, but some. But it will give you some confidence that, as crude as the assumptions that Semenov made, his and Frank Kamenetsky's theory actually works really well. Okay, and so here we have really, we actually want to find the sort of the temperature where this thing takes off. And so we have a nonlinear equation in temperature that we need to solve. And so if we want to find, so for a given ambient condition volume, convective heat transfer coefficient, and energetic material, which sets EA, rho, and Q, we can then solve for T to find the temperature values that actually lead to a steady state solution. Okay, and so graphically, you can think of it like this, is, let me scroll down a little bit, is recall that the heat the chemical reaction rate on a linear scale looks something like this, and this is due to the Arrhenius term. Right, so it has a curve that basically follows the Arrhenius term as a function of temperature. And for ignition, we are only interested in this portion here. And so if basically we are to look at what happens due to convective heat transfer, is basically the heat loss due to convective heat transfer would look something like this. Okay, and so graphically, there are three solutions, one here, and then basically a third one way up there. But for this ignition problem, we do not need to worry about this third point. Okay, and we only need to worry about these 2 points here. And so these are called stationary points, and these are the points where the heat gain due to chemical reaction is balanced exactly by the heat loss due to convective heat transfer. And you can notice that due to the curvature of the Arrhenius term in the low temperature region, there are actually two stationary points, and we need to analyze basically the properties of each of those stationary points. Okay, and so I just have a different graphical representation here. If you look at basically different heats of reaction, you can wind up with 3 different scenarios. Scenario 1, as I mentioned earlier, is where the convective heat loss curve and the chemical energy gain curve cross twice in this low temperature region. I talked about that one, and we will analyze that one. There's a third one here where the convective heat transfer loss is way too small, and the rate of chemical energy gain is always greater than the amount of convective heat transfer loss. And so in this case here, since Q dot of the reaction never crosses the heat loss curve, there is no steady state solution to this case because we cannot possibly balance this. And so that means, if we look here, that means if these 2 terms don't perfectly balance, that means the temperature is going to increase without bounds. And basically that is what a thermal explosion is. So in this case, in case 3, where you have either a really high heat of reaction or more practically a very small convective heat transfer coefficient, meaning you are not relieving the heat from your energetic material fast enough, basically no matter what temperature that you set the energetic material to, it will blow up. And we have the so-called critical case here, where it's basically just tangent, and then this temperature here, where it's tangent to the convective heat loss curve, that's called the critical temperature. Okay, and so there are 3 different cases, and remember, for all 3 of these curves, because we are interested in ignition, we are only interested in this very small portion of the Arrhenius term curve here. Okay, so are there any questions so far? Okay, so we'll do case 1, which was the red line in the previous curve. So basically, we had the convective heat loss curve, and if we assume that that the convective heat transfer coefficient is constant, then it's basically a perfectly straight line given by Newton's law of cooling, and the qualitatively the Q dot, or the heat gained by chemical reaction or burning of the material, is given by this curve here. And so now we want to find what is basically the properties of this solution. Okay, and so what we can do is we can start playing games with ourselves, is analyzing. So say if I'm going to analyze the properties of T1, there's a very formal mathematical way of doing that. But here we can sort of rationalize it sort of physically what is going to happen. So say we have a temperature that is less than T1. Okay, so say our temperature is over here of our system. Well, if we look at the curve here, the heat gain due to chemical reaction is larger than the heat loss due to convection. So basically what's going to happen is you have a higher amount of heat generated inside than you do heat loss through the walls. And so those terms are not balanced, and so the temperature goes up. And so it'll go up a bit more. And because of the shape of the Arrhenius term, basically the slope here is very flat. So as you increase the temperature, you don't increase the chemical reaction rate that much. But you increase the rate of convective heat transfer basically quite a bit. And so, but at this point here, the chemical reaction rate or the heat generation due to chemical reaction is still larger than the convective heat transfer loss. And so the temperature goes up, and you can keep playing this game. But if you notice, the difference between the heat generation due to chemical reaction and the heat loss due to convective heat transfer gets smaller and smaller and smaller. And what happens is the solution trajectory, say if we start here, it will actually go up along this line here until it gets to the stationary point T1. Okay, and so, but it will stop there because at this point here, it is perfectly balanced. And our ODE here for the rate of temperature is first order. And what first order means is that there aren't any inertia effects. So basically our system here, because it's first order, that it can't overshoot, it can't overshoot T1 and then wind up over here. So if it starts here, it will go nice and slow and stop at T1. Okay, so are there any questions with this? Okay, now we have region B here. What if the temperature is between our lower and our upper stationary upper stationary points? Well, here in this region, the rate of convective heat this case is the exact opposite. The rate of convective heat loss is greater than the amount of heat generated due to chemical reaction. So in this region here, say if I start the temperature right here, there is a greater amount of convective heat loss than there is heat generation due to chemical reaction. So then what happens is our system cools, and then the temperature goes this way. But still in this region here, the convective heat loss is higher. So essentially, I can basically go through the exact same argument that I did over here, but it's in the opposite direction. So no matter where I am between T1 and T2, as long as I'm not at exactly T2, the system will cool down until it hits T1, where the rate of convective heat loss and chemical heat generation are perfectly balanced. So if I could draw an arrow of the solution direction, if it was transient, it would run like this. Now, we have region 3. And region 3, or C, I should say, is this region over here. And this region here is just like region 1. And essentially here, we can go through the same argument, and the heat of reaction curve and the convective heat loss curve have the same signs as they did for the case over here. And so in other words, no matter where we are after T2, essentially we are generating more heat due to chemical reaction than we are removing by convective heat loss. And so the temperature goes up. Okay, and it will go up and up and up until we reach this third point here. But this third point is complete nonsense for these types of problems because this temperature at this point here would be about 10 to the 19 Kelvin. So, so for this type of problem, that is complete nonsense. Okay, so essentially what we can see here, what we have rationalized is the solution trajectory of our system would basically tend to, if it's going to quench or it's not going to blow up, it's going to tend towards T1, and basically this here is called a stable equilibrium point. If you've done any ODE system solutions in your classes, you had stable and unstable equilibrium points. And T1 is a stable equilibrium point, meaning that the solution is attracted to that point. And T2, since it is technically a stable point, that if you were to choose your system to exactly lie on T1, it would in theory stay at T2. Our system in theory would stay at T2 forever, but practically that is impossible, because if the temperature bumps, if either the rate of convective heat loss bumps away from it, or we have a slightly higher, even a slight change to the system, we are gonna knock it off of T2 one way or the other. And if we knock it even slightly to the temperature even slightly to the left and reduce it, the solution will then go towards the quench solution. And if we bump it to the right even a tiny bit, it will go to the thermal explosion case, where the temperature increases without bounds. Okay, and so this here is an unstable equilibrium point, or an unstable stationary point. They're sort of used interchangeably. So are there any questions with this? Okay, so yeah, this is what I just said. So I'm not going to repeat this, but this is just a graphical representation of what I just said. And so again, these T1 and T2, they are analogous to equilibrium points in mechanics, where basically T1, if this is a ball rolling down a hill, T1 is inside of a valley, and basically T2 is at the very top of the hill. Where in theory you could have you could have the marble just sitting on top of there perfectly, but it's not likely. And even if a slight breeze were to come and sort of push it even a tiny bit, it would roll one way or the other. Okay, so and so that's how those points work. And if you want to find them, if you actually want to find the values for these points, there's no by hand way of doing it, because our equation here is nonlinear. You need to use a nonlinear root finder to do it, and that is actually part of your homework. Is basically doing that. And I just recommend using the fsolve, whether you use Python or MATLAB. It's fsolve in both of them to solve it. And because you have two solutions right here, and I ask you to find both of them, you're going to have to actually find them both by basically playing with the initial guess. Basically, if the initial guess is close to T1, or say way over here, it will go towards T1, and if our initial guess is say way over here, it will tend towards T2. Okay, and so that's just sort of how you can find both of those stationary solutions with using the same root finder. Okay, so are there any questions with that? Okay, case 2, blue line. This is where the heat gained by chemical reaction was greater than the heat lost due to convection for all temperature. Thus, there is no stable solution possible, and only explosive states exist. So if you're designing a munitions depot, you want to stay away from this case at all times. Okay. And then case 3, the green line here, this here is called the critical case, and it's where there is only one crossing point for our chemical of our heat loss and our heat gain terms. And this one you can actually solve for this tangent point here exactly. Okay, and I go through the algebra here, and I'm not going to go through it in super detail. It is pretty straightforward algebra, and because it is a tangent point, not only and a stationary point, not only do we have the rate of heat gain due to chemical reaction and the rate of heat loss due to convective heat transfer, basically balancing each other out, but it's also a tangent point, and so we can apply another condition that the time rate or that the slopes of these two curves are also equal. And so I got it in the notes. I'm not going to go through it in super detail because it is fairly straightforward algebra. Is we just basically write them out, take a derivative with respect to temperature, and then basically solve, and then basically solve with these two equations. So I'm going to skip the details in the interest of time, but they're in the notes if you want to read them. But it's just a bunch of fairly simple algebra. Okay. And when you solve them, and you can eliminate a lot of the variables, here you basically wind up with a quadratic equation for this critical temperature in terms of the ambient air temperature. Oops, this should be infinity, not naught. And the activation energy of the explosive material. Okay, and so we can solve for that, and we wind up with P crit here. And so we just use the quadratic formula, and I just factored out. It's traditional in these expressions to factor out an EA over 2RU, and to get the solution into this form here. Okay, and so we can start to look at properties. And we demand that our critical temperature is not complex valued. That makes no sense. So we basically demand that the quantity inside the square root is greater than or equal to 0. It should be 0, not 1. And so that means that EA over RU, this here is called the activation temperature, has to be greater than 4 times the ambient temperature, and so which is easily achievable, because for a lot of explosives such as RDX, the activation temperature is over 23,000 Kelvin, and so I don't know what kind of environment you would have to be in where the ambient air temperature would be right around 6,000 Kelvin to cause this expression here to fail. But of course, if you subjected your explosive to a 6,000 Kelvin environment, something already went massively wrong to begin with. So you don't need to do you don't need to worry about that. And so so that's that. And also we can also find the maximum value of the critical temperature, and that's when the ambient air temperature is actually 1/4 of the activation temperature of the explosive. And just recall that EA over RU is equal to an activation temperature, and it's just the activation energy of the reaction divided by the gas constant, which has units of temperature. And so you'll sometimes see that being used, and that's called inactivation temperature. Okay, and then under these conditions, T crit is just equal to 1/2 of the activation temperature. Okay, and so here there is only one solution, if we are at this condition, because basically this here is, oops, wrong one. This here is 0, and then and then we have we only have one solution. Now, if this term here is less than 0, we have both roots to worry about, and you have two critical temperatures, and and for our cases, the lower value of the critical temperature is the physical root that you use for ignition or initiation, and the upper value is associated with extinction. If you have a burning particle, you can go through a Seminole analysis for that. And for that case, if you have a burning particle and you want to study how you can extinguish that burning particle, then in that case, the upper root is the one that is relevant to you. Okay. And I will just make a note here that that EA over 2RU is actually the inflection point of the Arrhenius term here. So here, the Arrhenius term here, basically prior to this, basically prior to half of the activation temperature, it's smiling over here, and it's frowny over here. And so, and that's just something to keep in mind when you're thinking of the properties of the solution. Okay, so are there any questions with that? Okay, so I did skip some algebra, but it's pretty straightforward. There aren't any really crazy games or anything like that that you have to play. So the Seminole theory, it is great qualitatively, and you can learn a lot about the properties of how a system ignites, and it can ignite and things like that. But there are some issues with it. One, it does not account for oxidizer. It does not account for depletion of the reactants, meaning that it assumed that YR was equal to 1 for the entire process. And so what effect does actually depleting the oxidizer, or does accounting for this reactant depletion, what effect does that have on a thermal explosion or not? In your guys' homework, you are actually correcting to account for that effect for Seminole. Okay, and the other thing is that we assumed that whatever shape our box was, and then no matter how small or how big, is that the temperature was perfectly uniform. That the temperature near the outer walls, where you have the heat loss occurring, is the same as the temperature in the very center. And and that bothered Frank Kamenetsky, and he corrected for that. Okay, and so the Frank Kamenetsky initiation analysis actually corrects for the fact that that there may be a different temperature in the middle of your material than there is on the outside. Okay, and so as I alluded to earlier, Seminole assumed that all variables in this chunk of energetic material are perfectly uniform. Is this physical? For some materials, it works well enough, but many energetic materials tend to be really good thermal insulators. So if you have a really good thermal insulator, and you have a heat generation source like you guys did in your heat transfer class, if you had a planar slab and you had some sort of Q dot occurring inside of it, you guys probably solve this one exactly, at least in class, and you'd find that basically due to the thermal diffusivity, the temperature profile would peak in the very middle of the slab, right? And so you have and basically, and they'll show that the equation accounting for the spatial dependence of temperature is a nonlinear heat equation. So a lot of the same physics still applies. So essentially, what you would expect then is that due to heating, due to the chemical reaction, you would expect there to be in the Seminole case, where that Q dot of the reaction would be basically spread out evenly because the temperature is uniform. Well, you're going to be generating heat, and so even if a Q dot is perfectly uniform, that to maintain a steady profile, that heat's going to have to basically conduct from the center out. And because there are more layers of material to go through, the center of the material is going to be at a higher temperature than the material at the edge. And so, and once you start playing with the numbers in your guys's like homework problem, you'll realize how sensitive these explosion initiation things are to fairly small changes in temperature. And so just the fact that even one little portion of the domain of your energetic material is at a slightly higher temperature, that means it could potentially easily run away from basically run away and thermally explode. Okay, and so how do we account for this? This case here. So first of all, our starting point is not going to be a control volume analysis. Our starting point is going to be the full energy equation in temperature form that we derived earlier. And we're going to assume that the density is constant. We're going to assume that the pressure is constant. We're going to assume that there's no fluid motion. All thermal physical properties will be the same. We'll assume that the solid is incompressible and that we can approximate Cp and Cv as the same value. And we'll be examining ignition. So we are also going to assume that YR, or that the mass fraction of the reactants is equal to 1, and the rate of production of the rate of production of the reactants is the exact same as it was for the Seminole analysis. Okay. And so this means that the basically mass fraction for all the species is basically roughly constant. And we're assuming that our chemical reaction is R goes to P. Okay, and so we just have two species, some reactants and some products, and the density of both the reactants and the products are the same. Okay, so it's the same problem, only we are assuming a non-uniform temperature profile. That's it. So here, to derive this equation, we can treat our conservation of energy that we worked hard to derive in your homework. We can use that as the starting point. So here, there is no flow. So I just wrote that out, and I just started crossing out terms. So there is no flow. V is 0. So basically, the advection term of temperature, that goes away. We're assuming constant properties, so we can yank out thermal conductivity. We're going to neglect the Dufour effect completely. We are going to, there is no flow, so there is no viscous dissipation here. So that goes away. Here we have no, this term here is 0. And the reason it's 0 is because the mass fraction of the reactants is always equal to 1. And that implies that the gradient of the mass fraction, if a mass fraction is constant, the gradient of the mass fraction is 0. And if the gradient of the mass fraction is 0, that means the diffusion velocity is exactly 0. And so this term here goes away too. We need to retain this this chemical heating term, and we are assuming constant pressure, and so this pressure term here goes by 2. Okay, and so you can see is that we start from our master energy equation here, and we just start crossing out the terms that we don't need anymore. And so when we do that, based on what was set up here, we have rho Cp partial t partial time times lambda times the which is the thermal conductivity times the Laplacian of temperature minus the, or actually plus plus the chemical heating term here. Okay, so are there any questions with this? Okay. So then we can divide both sides by actually rho Cp to get the time rate change of temperature by itself. And we have lambda over rho Cp. Well, that's just the thermal diffusivity. So I'm just going to call that alpha. And we have 1 over rho Cp times this chemical heating term. So you can do the exact same thing that we did for Seminole. You can actually expand out the sum into the products in the reactants, because remember that our chemical reaction is R goes to P, and we only have 2 species. So this would be, and so the sum here is omega dot R times the enthalpy of the reactants plus the rate of production of the products times the enthalpy of the products. And recall that the sum of omega dot I has to be equal to 0. So that means omega dot P equals minus omega dot R. Okay, and so we basically go through the same steps that we did that we did for Seminole, that we basically substitute in omega dot P equals omega dot R. That allows us to factor out an omega dot R, and then get this enthalpy difference between the products and the reactants. And because we are assuming constant Cp for all species, and I showed this in detail for basically Seminole, this just basically this quantity here just becomes your heat of reaction. And then our chemical heating term here is simply minus rho A times Q times e to the minus EA over RUT. So same as it was for Seminole, with the exception that in front of it there is a 1 over rho Cp. So basically this row here and this row here cancel out. So our transient Frank-Kamenetsky equation is right here, and this is the fella that that I'm asking you to modify a 1D transient heat conduction code with constant heat generation to solve this equation right here. Okay, and so that's part of your homework, is basically converting the equation where basically this is just a uniform Q dot into basically this form right here. Okay, and so for this class, we will assume this works for multidimensional scenarios. And if you want to see if the solution is going to explode or not, you basically just solve this equation using your favorite solver, and just marching it in time and seeing whether this solution runs away or not. Okay, but and so that will work for an explosive of any shape. This is a multidimensional simulation, or a multidimensional equation. So in principle, you could have an energetic material shape like this, and you could do Frank-Kamenetsky on this energetic material if you so choose. I'm not aware of anybody who does that, but they usually consider simple shapes. And in this class, we will not be working with the full multidimensional version of this, because I can't assume that you guys have had heat conduction where you solve this numerically, I think, or a numerical methods class. So, or I should say a graduate level numerical methods class. So in this class, we will assume that we are going to be working in one dimension, and in one dimension, the Laplacian of temperature, you can show that it is equal to the second derivative of temperature with respect to space plus a kappa divided by x times partial t partial x. And kappa is our coordinate system selector. If kappa is 0, we have a planar slab configuration where we have just an infinite sheet of explosive. If kappa is 1, it is an infinitely long cylinder. And if kappa is 2, it is a perfect sphere. So I'm defining x in these cases to be from the center of the object, whether it's a cylinder or a sphere, and x is basically pointing in the positive direction, basically towards the outer wall. Okay, and so for the cylinder and in the sphere cases, x would be our radial coordinate. Okay, and basically R naught is the half thickness of our planar slab, or it's the outer radius of the sphere or cylinder. Okay, so are there any questions with this? Okay, so then I'm going to take this here and I'm going to substitute it in. And our 1D transient Frank-Kamenetsky equation is basically right here. Okay, and so we want to solve this equation and we want to see whether our system is going to blow up. So this is a partial differential equation and it's transient, so we need boundary conditions. And because we have a second derivative of temperature, we're going to need 2 boundary conditions. And basically here, the classic Frank-Kamenetsky solution, he uses a constant wall temperature. Okay, so he uses a constant at the outer radius. He just uses a fixed wall temperature. Okay, and then for the second boundary condition, we can note that at the very center of our object, the solution must be symmetric or bounded. Okay, and so it must be a finite value, and it must be symmetric. Okay, and so but it's very common to solve this Frank-Kamenetsky equation here, where we replace the fixed wall temperature basically with a convective heat transfer boundary condition. Okay, and so our boundary conditions are here, and I'm going to define t as a function of space and time. So we want so at the center we basically want symmetry or bounded solution. Okay, and so this just means that the temperature gradient at the center of our material is 0 for all time, and so that would be at the center. Then we got our boundary condition at on the outside, and that means the temperature at the outer wall at all times is equal to some T naught, and that would be just a boundary condition that we are applying to the outer wall of our object. So I'm going to call this T naught. Okay. Or what is done quite often too is you can use a convective heat boundary condition, where basically the rate of convective heat loss through the surface has to be equal to the rate of heat conduction on the very outside. Okay, and you guys have basically worked with this in your heat transfer classes to derive this boundary condition, and you may have even sort of played with it for some cases. Okay, and so this would be a convective heat transfer boundary condition, and we have our initial conditions. And sometimes in the classical case, he will start the solution. He will start the initial conditions at the wall temperature. or TR, it's a classic case, yes, you will start the solution at some wall temperature and at some general initial temperature in general. So, and so, yeah, and so those are the initial and boundary conditions. So are there any questions with this? So here with Frank Kamenetsky, it is no longer a zero-dimensional solution. It is almost the same as the Semenov, except for Semenov, we did not have this heat conduction term here. And so with this heat conduction term, that adds a spatial dependence to our temperature profile, and so we can account for the non-uniformity of temperature in our object, and things like that. But the source term, due to heat, is actually more or less the same. It's just rearranged a bit differently, where I divided by basically rho Cp on both sides to get it into this form here. Okay. So, are there any questions with this?
So with that equation is basically all of our Q and temperature are both functions of space and time.
This Q here is just
that's
a property.
Constant.
Yep, that's a constant.
So we just have temperature as a function of space and time.
Yes, but Q dot, which is this term here, that is a function of space and time. And that's due to this Arrhenius term here, which is a function of temperature. Or you can write it as Q dot is a function of temperature, which is in turn a function of space and time. Does that make sense?
Yeah, that makes sense. I was just, you could solve this by hand then.
No. You in this form you cannot solve this by hand, and that's because of this evil, nasty Arrhenius term here.
Okay, I was thinking you may just be able to treat that as a generation term, as a function of x and t.
It is a generation term of x and t, but it is extremely nonlinear.
Gotcha.
Yeah, and you need to more or less linearize it to be able to solve it, and even the linear case leads to an obscure partial. If you assume steady solution, it leads to and you simplify this Arrhenius term here, it still leads to an obscure partial differential equation that you have to solve, that I never heard of till I started going through these notes again. Okay, and so in general, due to the nonlinearity of the chemical source term, the PDE, you have to solve it numerically. There's no getting around that. However, Frank Kamenetsky did not have a computer, but all he wanted was an ignition criterion. And again, he assumed that the mass fraction of reactants was equal to 0. Again, we're only looking at ignition, so if the mass fraction of the reactant starts depleting rapidly, we have ignited. And our problem is done. And so, and again, as noted by Vince, this equation is really just a 1D heat conduction equation with a very nonlinear heat source term. And the most difficult term is this Arrhenius term right here. And so Frank Kamenetsky was interested in ignition, and this is part of where, if you're a theoretician, and you get to this equation here, and you want to solve it by hand, you need to start approximating it, and you need to use their physical intuition. And I'm going to go a bit longer by a few minutes just to make up for basically what the fiasco of Wednesday is. Basically, a theoretician will apply their intuition to basically come up with ways to simplify the problem. And Frank Kamenetsky was interested in ignition, and he noticed that the maximum temperature in your energetic material minus the subtracted from the ambient wall temperature was no more than, say, 20 Kelvin, 50 Kelvin at most. If it's higher, if the temperature is sort of higher than this range, it's going to blow up. And so what he then realized is that the basically ratio of the maximum temperature rise in your system, that's what this term is, divided by the initial temperature, which will be on the order of 300 Kelvin, is fairly small. Okay, and I'm being overly conservative here. The maximum rise in temperature is normally smaller than say 20 Kelvin. Okay, then if we define some Q, I don't know why I use small q as my throwaway dummy variable to simplify things. We can define Q as this temperature ratio, and then basically solve for T. And so we know that we have this expression here for T, and we got it in terms of Q, which sort of gained me nothing. But in the Arrhenius term, we have this EA over RUT, and I can substitute in this expression here, and I get EA over RUT naught times this 1 plus Q. And this Q is small, but it is not 0. So we have, and so what we're going to do to simplify this term is we're going to expand 1 over 1 plus Q in a Taylor series. And if you do that, we get this Taylor series expansion here. You can ask Mathematica to do that for you. Or this is a very common one that you guys did in your Calc 1 class, either in high school or in freshman calculus. Okay. And so, oops, not Z, Q. And so Q is small, but it is non-zero. So we can't just stop it here. We need to basically take these first two terms here. Okay. And so if we substitute basically this approximation in, that basically 1 over 1 plus Q is approximately equal to 1 minus Q. So basically this inverse temperature that goes in the Arrhenius term is greatly simplified. And so then EA over RUT is equal to this. I just substituted in our Taylor series for basically 1 over 1 plus Q. And I substituted in the definition of Q. And I can basically factor out, basically put this in, sort of expand this out. And then what we really want is e to the minus EA over RUT. And that will approximately be the exponential of the minus of this term, which is this, and then multiplied by the exponential of basically this term here, which is minus is plus. So it's e to the EA over RU times T minus T naught over T naught squared. And in this term here, we still have an exponential with a temperature in it, but the temperature is in the numerator, which makes it a lot easier to deal with. Okay, it's the fact that a part of what makes it super nasty is the fact that in the Arrhenius term is that the temperature is in the numerator of the argument, and so there's sort of a double whammy effect here. You have the nonlinearity due to the exponential term, and you have a nonlinearity inside of that nonlinearity due to the 1 over temperature dependency for its argument. Okay, and so then essentially he basically substitute this in, and I will stop for the day. I just wanted to get past this Taylor series stuff, and you'll see Taylor series being used from time to time in this class, and it's mainly used by theoreticians wanting to solve things by hand because they can't solve this full equation here, even if it's steady, is impossible to solve by hand, and that's because of this culprit right here. Okay, and so that's it for today. Are there any questions?
I just had a quick question about the homework,
Mhm.
specifically the Python.
Yep.
Do we have to do the conda combustion thing every time we want to open a new like Jupyter notebook?
Yeah, because essentially it is what the conda activate combustion thing is doing is it is isolating all the packages that you that you need to do this sort of combustion stuff, and you may have a separate installation. Like their example was baked beans or something like that, um, and so but you don't have to do that. It's just a nice way to sort of containerize different instances of Python. And if you already have Python installed, just install Cantera with your existing installation. And if you're used to, and you don't have to use Conda. It's just if you've never installed Python before, with Conda, you kind of just keep pushing next like 5 times, and it'll be installed. Usually without a hitch.
Okay. So yeah, because I've never used Python before, so I was very confused if we should open it using the terminal each time, or should we, if like just we had to do that once and that was it.
You do, at least on Mac and Linux, you do have to open it from the terminal basically all the time, using conda activate whatever the name of your package is, and then either Jupyter Lab or Jupyter Notebook to basically fire up the calculations.
So there is if you did download it through Anaconda and you have the Anaconda GUI, the app on your Mac, you can open up the environment within the app. You can scroll in, click the combustion environment, and then you can even click on Jupyter Notebook within that. And that's a way to open it without going through the terminal. But I wouldn't say it's easier to do it that way. It's just, you can open up Jupyter Notebook within combustion environment through that route.
Oh, okay.
Then if there's anybody who has experience with any gotchas with Windows, please speak up, because I use Mac, so I use Mac or Linux, so I don't know if there are any weird gotchas with Windows.
Yeah, I'm just using it on Mac as well.
Okay, and nobody is piping up, so they're either Mac users or they've had no problems, or they haven't looked at it yet. So, but yeah, and so the third problem in the homework set will require upgrading Seminole analysis to account for oxidizer depletion. And when you do that, you have to do transient. There's no steady state solution for that. And so that means you need to solve a set of 2 sets of stiff ODEs. But you solve ODEs in Python if you go through my Python, my probably pretty dry Python Jupyter notebook, which I describe, which I walk you through it on a YouTube video that I posted on this channel. You'll see I'll show you how to do that, but it's a lot like MATLAB. The command is a bit different, and then root finding is basically almost the same fsolve. And there are some nice things with it. Is that in MATLAB it drove me insane. Is that if you have a project with say 20 different functions, and half those functions are small, like 2-line functions, they all have to go in their own M file. I don't think that's the case anymore, but back in the day that actually was the case, and so project files got very, very bloated because you had all these tiny little files for a bunch of little 1-line functions, and so that kind of drove me nuts with MATLAB. So, but Python, if you know MATLAB, you can pick up Python pretty quickly. And so, yeah, if anybody wants to chime in on their experience with basically with that, feel free to do so. Okay, and so